Good morning, all.
Good morning, sir.
In the last session, we discussed about the CMOS TTL interfacing. So, how a CMOS outputs drive the TTL inputs, and vice versa. How the TTL outputs can drive the CMOS inputs. So, here for interfacing, in the interfacing of CMOS and TTL, so we have used the extra circuit elements like a pull-up resistor or a level shifter or a level translator or an inverter, sorry, and buffer are the tri-state buffers. So for interfacing of the TTL to the CMOS and CMOS to the TTL, so we are using the extra logic elements or the extra circuit elements to translate the output levels of the one gate to the another gate, or from one logic family voltage levels are translated to the a compatible state of the other logic family. So in the last we have seen that the CMOS and TTL interfacing. In today we will discuss low voltage CMOS logic, low voltage TTL logic, and its interfacing here. So here the point to remember that for interfacing of one logic gate to the another logic gate, or interfacing of the one logic family gates to the other logic family gates, we require extra logic elements or extra circuit elements such as the pull-up resistors or the tri-state buffers or the buffers and the level shifters or the level translators. So coming to this low voltage CMOS logic and interfacing. So as of now seen, so we have seen the interfacing for the normal CMOS logics are the higher voltage of the CMOS voltages. So normal CMOS logic voltages are operated with the 5 volts of the power supply, or the higher voltages CMOS circuits are operated with the voltage of the 15 volts, and the standard or the normal TTL logic gates are operated with the 5 volts of the power supply. So till now we have seen the interfacing for that kind of logic circuits in the CMOS and TTL standard logic levels. So now what is this low voltage CMOS logic level, and why the low voltage CMOS are the low voltage TTL logic here? So there are two important factors which have led the IC industries to move towards the lower power supply voltages because of the two important factors. So because of the two important factors, the lower power supply voltages, in CMOS circuits, especially in CMOS circuits, are demanded here. So what are the two important factors here? The first one is the lower power supply voltage reduce the dynamic power dissipation more than the proportionally here. So if you use the lower power supply voltage, that reduces the dynamic power dissipation of that logic gate here. So in CMOS outputs, the output is switching between the power supply rails here. So that is, it is switching between the high state to low state and low state to high state. So during the high state, the voltage will be, the output will be switched to the VDD. During the low state of the output voltage is switching, or the output voltage is switching to the 0 volts here. So in CMOS outputs, the output is switching between the maximum and minimum of the power supply rails. And even if you see the dynamic power consumption of the CMOS logic, the power consumption is given that CV square F. So do you remember this equation? The dynamic power dissipation in CMOS logic. We have seen that the CV square F. So here the C is the load capacitance, or the it is the load capacitance value, and it is the power dissipation, the power dissipation because of the transitions at the input, and the V is the power supply voltage, and F is the frequency of the output transitions, or the transitions of the output frequency at the output signal. So the dynamic power consumption is CV square F. So now you can understand from this equation that the dynamic power consumption of a CMOS circuit, it is proportional to the power supply voltage V. So now you have a higher voltage, say 5 volts here. So now the dynamic power consumption is proportional to this 5 volts of the power supply, because the stray capacitance at the output of the gate circuit has to be charged to the power supply voltage VDD during the high state, that is the transition from 0 to 1. And while the output is transition from the 1 to 0, that is from high state to 0 state, the stray capacitance at the output gate, they has to be discharged to the minimum value 0 volts. So when your operating voltages, or when your power supply voltages are at higher voltages, with this dynamic equation, you can understand the dynamic power dissipation is more when you are using the higher power supply voltages here. So now if you cutting down the power supply voltage, if you cutting down the power supply voltage, so now what will happen? So now the power supply voltage is reduced to 3 volts. Now the power supply voltage is reduced to 3 volts, say. So now what is the power dissipation now? For the 5 volts, with respect to for 5 volts, the power dissipation will be more, and with respect to the 3 volts, the power dissipation will be less, and which is quite small even with the proportional value also. So therefore, the lower power supply voltage reduce the dynamic power dissipation. So that is one advantage if you have a lower power supply voltage here. And the second important factor is the lower power supply voltages allow to have the smaller transistors geometries. The lower power supply voltages allow to have the smaller transistor geometries here. Just a second. Just a second. Just a second. So the second important factor is the lower power supply voltage allowed to have smaller transistors.
Green screen వస్తుంది సార్.
Amma?
Green screen మధ్యలో వస్తుంది సార్.
Just a minute. Okay, 1 second. అమ్మా ఇప్పుడు ఎలా ఉంది? వస్తుందా? విజిబుల్ గా ఉందా?
వస్తుంది సార్ ఇప్పుడు బాగానే.
So the second factor is low power supply voltages here. So when you have a low power supply voltages, so here the oxidation between the gate of the transistor and between the source and drain. So if you see the structure of an N channel or the P channel transistor, say take the structure of a N channel or P channel transistor. So you will have a P channel, and on which you will deposit the N channel, and there will be a sorry. So you have a P channel substrate, and on which you have deposited two N regions, and so there is a gate terminal, and which is separated with the dioxide layer, this is the gate, and say the source and drain, say. So now, so for this lower power supply voltages, the channel length of the transistor will be less here. For a moderate or for normal values of the channel length, if you take, they require a minimum of the power supply voltage is 5 volts here for the normal channel length of the transistor. What do you mean that channel length? It is the difference between the source and destination. The difference between the source and destination is called the channel length of the transistor. So for normal power supply voltages, the channel length is the moderate value here. It is with the normal values. But for lower power supply voltages, so if you take the normal channel length of the transistor, it is incapable of handling the such lower power supply voltages for this channel length of the transistor. So for lower power supply voltages, we will have the lower channel length for the transistor. When we have the lower channel length, so that results in the transistor in the smaller size. When the transistor results in smaller size on the semiconductor dies, the number of transistors per the gate can be increased. So which means that the density of the IC can be increased if you have a lower power supply voltages here. So with these two parameters, one is with the lower power supply voltage, it reduces the dynamic power dissipation. And the second parameter is the lower power supply voltages allow to have the smaller channel lengths so that the transistor size can be decreased here. The transistor size can be decreases here. So as a result of these two factors, so here the JEDEC, which is the Joint Electron Device Engineering Council, which is a standard industry group. It is a standard IC industry group selected 3 power supply voltages as the standard power supply voltages for the lower power supply voltages. So this JEDEC, Joint Electron Device Engineering Council. So this has given 3 power supply voltages and as a low power supply voltages here. So they are the 3.3 volts and 2.5 volts, and the another voltage range is 1.8 volts. So now what are the operating voltages now? For 3.3, there is a tolerance value plus or minus 3 volts. So the maximum voltage can be 3.6 and the minimum voltage that you can consider for the logic is 3 volts. So now the operating voltages are between the 0 to 3.3. Standard value is 3.3. It may be have a higher and lower values with the tolerance. And the second range lower power supply voltage is 2.5. So which means it has an accuracy, it has a tolerance value of plus or minus 0.2. So the maximum 2.7 and the minimum is 2.3. So now the operating voltage is 0 to 2.5. 0 to 2.5. This is the operating voltage range. And the another low power voltage range is 1.8 volts here. So now you can, this also has an tolerance value. The maximum is 1.95 volt and the minimum is 1.65 volt. As a standard value, we will take the 0 to 1.8 volts here. So now what are all these here? So these are all the standard low power supply voltage ranges. We have a voltage range of operating voltage have the 0 to 5 volts, isn't it? So this voltage range is normally using as a standard operating voltage for the CMOS as well as the TTL also. And in the case of CMOS, we have the higher voltage ranges from 0 to 15 volts is also available for the CMOS cases. But now we have, in addition to these two, now we have the another power supply range, which are the lower power supply voltages. And there are three types of the voltage power supply logic levels are available. They are 3.3 is a 1 voltage logic level, 2.5 is a another logic voltage level, and the another low power supply voltage logic level is 1.8 volts here. 1.8 volts. So now if you understand this, in CMOS, we have a low voltage logic and the standard voltage logic and the high voltage logic. The low voltage logics are these three voltage logic levels, and the standard is 0 to 5 volts, and the higher voltages of the CMOS is 0 to 15 volts here, right? And for the case of TTL, we have standard operating voltages are 0 to 5 volts. Now we will have an additional voltage logic level is 3.3 volts here. So do you understand this? For TTL, you have two different logic levels, 0 to 5 volts and 0 to 3.3 volts as a low voltage TTL. Whereas for CMOS, we have three logic levels. What are the three logic levels? Low voltage logic levels. In the low logic voltage levels, we have three different logic levels are available. And the standard is 0 to 5 volts. And the higher CMOS voltages are operated between the 0 to 15 volts. So these are all different logic voltage levels with respect to the power supply voltages. Now what is the problem with all this here? So some of the CMOS gates and some of the TTL gates, they will be operating with the 0 to 5 volts. And some CMOS logic gates, especially they use the high voltages here. And some of the CMOS and TTL logic gates, they use the 3.3 voltage levels. And some CMOS gates use the 2.5 and 1.8 logic gates here. So now what is the problem that can arise here? The problem is compatibility. So here the problem is compatibility. So here the lower voltages has to be compatible with the higher power supply voltages here. So in order to do this compatibility or to connect the lower voltages logics to the higher power supply voltages devices, so there are two basic approaches are used here. So to interfacing the low voltage CMOS or low voltage TTL to the high voltage of 5 volts of the CMOS gate or the 5 volts of the TTL gate. So if you want to do this, so here there are two approaches are used here. So one approach. So in this approach, the devices operate and produces the low output voltages. So the devices will be operated with the 3.3 voltages and they will be producing output according to the 3.3 voltage logic levels. But these low voltage devices can also tolerate the inputs at the higher supply voltages. They will be operated with the low voltages and they will produce the low output voltages, but they have a tolerance. They can tolerate the high inputs at the high supply voltages here. So that is one approach for interfacing of the low voltage logics to the high voltage logics or the standard logic values. And the second one is, so this is the second approach here. In this second approach, the devices are provided with the two power supply voltages here. In the first approach, they will be operated with the as per the given logic levels, but they have an additional feature that they will accept the high supply voltage inputs too. That is the first approach method. In the second approach, the logic devices are provided with the two power supplies here. They are provided with the two power supplies here. So between the two power supply, one is one is low power supply voltage, one is low power supply voltage, and the other one is high power supply voltage here. The low power supply voltages are nothing but 2.5 volts. They will be operated with the 2.5 volt logic or 1.8 volt logic here. One of the power supply. And the second power supply is, it is operated with the 3.5 volts here, because the 3.3 power supply voltage has a tolerate inputs at the higher supply voltage. So in the second approach, we use two power supply voltages. One power supply is 2.5 volt, and this 2.5 volt is used to operate the internal gate structure. So the internal logic gate will be, and the outputs are operated with this 2.5 volts. Where this 3.3 volts, it will be used to handle the external inputs and external outputs, because the external inputs and outputs are the high voltages. So here we use the two power supplies here. A low voltage is supplied to operate the internal gates. So when it is operating with the internal gates, this is said to be the core logic here. So one supply voltage is for core logic to operate the internal gates and outputs, and the second one is the high voltage is supplied to operate the external inputs and the outputs. This is said to be the pad ring logic here. So these are the two basic approaches. In one approach, the higher supply voltages will be accepted at the input. In the second approach, we using the two power supply voltages. One supply voltage is for core logic and the other high power supply voltage is for the pad ring logic. They are pad ring logic here. So now let's see the standard and the low voltage CMOS logics in a single diagram. So here see the logic levels for the standard and the low voltage logic families. So now from the figure A, if you see from the figure A, it is the 5 volt CMOS logic. So it is a standard 5 volt CMOS logic where it is operating between the 0 volts to 5 volts, and in that range, so the 4 voltage parameters are defined here. The 4 voltage parameters are defined. This is the threshold voltage in defined state. So it is a undefined state here. So the 4 logic voltages VOH, VIH, VIL and VOL. And the figure B also the standard TTL logic family here. So the standard TTL logic is operated between the 0 to 5 volts, and in that range, So the logic parameters are defined here, the VOH, VIH, VIL and VOL. So now the figure A and B are the standard CMOS and the standard TTL logic family, logic levels. Now, just now rightly we discussed that there are three standard low voltage families are available. What are the three here? The one is 3.3 voltage logic and 2.5 voltage logic and 1.8 voltage logic. And here in this 3 voltage logics, the 3.3 voltage logic can be used for both TTL and CMOS devices here. They can be used for both TTL and CMOS devices. Whereas the 2.5 volt and 1.5 volt, they will be exclusively used for, So here the 2.5 volts and 1.5 volts, they will be exclusively used for CMOS logics here. They will be exclusively used for CMOS logics. Whereas the 3.3 volts, it can be used for CMOS as well as TTL here. So that's why these are named as low voltage CMOS, low voltage TTL, 3.3. And the 2.5 is only for the low voltage CMOS and the 1.8 is also for the low voltage CMOS here. So I think you can understand this. So the standard logic levels are 0 to 5 volts and the low logic levels are three types: 3.3 volts, 2.5 volts and 1.8. And within the 3.3 is for the CMOS as well as the TTL. Okay. And for the 2.5 and 1.58 volts they will be exclusively for the low voltage CMOS. We cannot use these logic levels for the TTL because the TTL cannot accept these logic levels here. Right? So now we will discuss the 3.3 voltage logic family. 3.3 voltage logic family. So now if you observe here, let's take the standard 5 volts of the TTL family. So now if you see what are the values of the VOH and VIH and VIL and VOH, these are the same as of the 3.3 volt low voltage TTL family, isn't it? Right or wrong? So here the VOH of the standard TTL and the 3.3 VVL VOH is 2.4. These two are same. So here there is no problem or there are no difficulties for interfacing the standard TTL logic voltage to the 3.3 voltage low voltage TTL family and vice versa. The low voltage TTL logic families can be interfaced to the 5 volts of the TTL logic families because these two are having the same identical logical values here. So that is low voltage TTL here. Low voltage TTL. And even if you take the low voltage CMOS here, when you take the low voltage CMOS, the DC loads of the low voltage CMOS or the standard CMOSs are very small here. The DC loads are very small because the CMOS inputs and outputs will take a very low amount of the currents here. Especially for the CMOS inputs, they will be handled with the very small amount of the currents. So for the low voltage CMOS in this 3.3 volts, there are no difficulties to interfacing the LVC CMOS to the standard CMOS also. Maybe the difference may be of a 0.2 voltage drop, so that will be easily handled by the devices. So here we have seen now the 3.3 voltage logic. And how do we interface these devices here? In the last session we have seen, so how we can interface by taking off an extra pull-up resistor, or by using the level transistor, or by using the level shifter, or by using the tri-state or buffers. Tri-state buffers or the buffers. So the interfacing is same here. And coming to the 2.5 volts here, whereas if you see the 2.5 volts and 1.8 CMOS logics, their VOH and VIH, VIL and VOH are very small here. The power supply voltage itself is a 2.5 volts. It is a smaller value. And within that range, they have defined the VOH, VIH, VIL and VON. So these are very small voltage logic levels. Now if you see for the 1.8, there are much smaller than the 2.5. The 2.5 is smaller than the 3.3, and the 1.8 logic voltage levels are smaller than the 2.5 logic values. So now how we can interface the 2.5 and 1.8 logic gates to 3.3 voltages or the 5 voltages of the standard logic power supply voltages. So for that we will use level translators, level shifters. So the level shifter takes the low voltages from the 2.5 and 1.8, and they will be translated to the required level of the 3.3 and 5 volts here. So therefore they can be easily handled here. So that is what we can see in the next slide here, the 3.3 voltage logics. So this logic defines the two sets of the logic. We have already discussed here. See, the low voltage CMOS and the low voltage TTL. So in the low voltage CMOS, there are no difficulties because they can be easily compatible because of the low DC loads at the output. Whereas for the low voltage TTL levels, so here the 5 volts of the TTL has the identical values with the 3.3 voltages here, logic level. So you can see here in diagram, this one, the 5 volts of TTL and 3.3 volts TTL. So these are all same here. So there are no problem with the case of the 3.3 here. But in the 2.5 and 1.8 logic, if we take, so here the logic voltage levels are smaller than compared to the 3.3 logic. So therefore here we need the level shifter or the level translator is needed here. So the function of the level shifter is it takes the lower voltages and it will be translated or it will be shifted to the compatible values of the higher supply voltages here. So this is about the low voltage CMOS logic and TTL logic here. TTL logic. So do you understand this? And here, if you see in the first slide of this, if you see here, so there are two basic approaches. One is tolerate of the input values, and second one is the two power supply voltages. So far what we have seen is the second case here, using the level shifters, using the level translator with the two different power supplies, we can interface the lower logics to the higher logics here. Now what about this case here in the first approach here? So they will have some modified logic circuit so that the lower voltages logic circuits will accept the high input power supply voltages here, high voltage power supply voltages here. So in this PPT I haven't shown this. So I will just show the two diagrams. Just a minute. So here you can see here. So here you can see here. So this is the CMOS inputs of non-5 volts tolerant. So non-5 volts tolerant. Is it visible to you all?
No, sir.
Sir,
It is not visible.
not visible, sir.
Sir.
Just a second. Now is it visible?
Yes, sir.
Yes, sir.
Yes. So now here you can see the how the CMOS logic circuits can tolerate the high input voltages here. So now if you see this first circuit diagram, which is for the HC and HCT here. High speed CMOS, high speed CMOS TTL. So where they are operating with the 5 volts of the power supply only. So now in this circuit configuration, if you see, there are two protecting diodes D1 and D2, which are usually at the input circuit. They will be commonly used at the input circuit here. And what is the purpose of the D1 and D2? When the higher voltage is flows in the circuit, or when the higher voltage is flowing at the output. So this D2 diode is easily forward bias because the VCC is 5 volts, say, and the V1 is 6 volts, say. So now the V1 voltage at the D2 is forward bias because the voltage at the V1 is 6 volts and the VCC is 5 volts. Therefore, higher voltages are easily bypassed. Okay. And similarly, if the negative transitions are happened, if the negative transition is there, so that excess negative is bypassed by this D1 here. So this will be reverse bias. So therefore, the excess bias, the excess voltage will be grounded here, which means the D1 and D2 are protecting the input circuit from the higher supply voltages here. So now how the lower supply voltages can accept the higher input voltages here. Now see the second diagram B. So here this accepts the 5 volts tolerant VHC here. What do you mean that VHC? VHC is very high speed CMOS here. So now by eliminating, by removing this D2 diode, this circuit will accept the higher input voltages. What is the case in the diagram A? If the excess voltages are flows, so that will be bypassed by this D2 by forward biasing this diode. Now if you remove this, the excess current or the excess voltage can be reached to the circuit if you remove this D2 diode. So that is how the circuits are operated with the low voltage and it produces the low voltages, but it can accept the high input tolerant voltages. Okay, that is with respect to the input. And now if you see for the second case at the output here, if you take for the output here, so now here you can see for the output. So usually here it is the output where you will take the output at this point here, at the output of the gate here. So now to accept this excess, to accept or to tolerate the output voltage at the output gate, so there will be extra P channel is used so that we can tolerate the higher output voltages at the output. So these are the cases. These are the cases for the first approach here. Okay, just a second. So now we will go to the normal PPT. So is it visible here? Is it visible?
Yes, sir.
Yes. So this is about the low voltage CMOS logic and low voltage TTL logic. These concepts are very easy. The only thing is how the logic levels are shifted to the required levels of the next logic level. I mean, at input you have CMOS, at output stage you have the TTL. So now the CMOS voltages are higher than the TTL. Now there is no problem, the CMOS can easily handle the TTL. Say, now the reverse case, if you take the TTL having the lower voltages, but the CMOS is having the higher input voltages here. So now it is difficult for the TTL circuit to drive the CMOS circuit here. In such cases, what we will do, we will use the pull-up resistors, or we can use the level shifters, or we can use the buffers. Therefore, the buffer we can increase their output currents, so the output currents can easily handle the circuits, or the voltage will be shifted to the lower voltage to the higher voltage. So therefore, the buffer output can easily handle the CMOS outputs. I mean the CMOS input gates. Okay, so this is about the low voltage CMOS logic interfacing. So till now we have discussed. So till now we have discussed the CMOS logics, CMOS logic gates, CMOS logic behavior, BJT logic. In BJT logic, we have seen the TTL logics and TTL logic gates, and the interfacing of the CMOS and TTL, and the interfacing of the low voltage CMOS and low voltage TTL. So this is all about the TTL logics and the CMOS logic. And the next one is, the next type of logic is emitter couple logic here. Emitter couple logic. So here the emitter couple logic is based off the bipolar logic family. It is one of the bipolar logic family. And the advantage with this emitter couple logic is it is the fastest of all logic families. Even from the CMOS also, it has the fastest speed. It is a very fastest logic family here. And in this emitter couple logic, we use the differential amplifier configuration. You know the differential amplifier configuration. Two transistors are connected in parallel here. Two transistors are connected in parallel. And the emitter of the two transistors are connected commonly. Okay. And the transistors are operating in active and cutoff regions. So unlike in the TTL logic family, if you see, in the TTL logic family, the transistors were operating in the cutoff region or saturation region. So when the transistors are operating in the saturation region, they will experience the storage delay time. They will experience storage delay time here. Okay, so because of that, the propagation delay of the circuit will increases if the transistors are operating in the saturation region. But in emitter couple logic, the advantage is the transistors will never go into the saturation region. They will always be operating either in the active region or in the cutoff region here. They will be operating in the active region or in the cutoff region here. And since the transistors can be operated in the active region, or the transistor is operating in the active region, it has the fast switching in the active region. So the transistor will be operated very fastly, because it can't go into the saturation region. So if it is going in the saturation region only, you are having the storage delay, thereby you have a propagation delay. But the transistor is operating in the active, since it is in the active region or it is in the active mode, so it has the fast switching speed here. So thereby the lower time delay here. So when the output is switching fastly between the states from 0 to 1 and 1 to 0, the time delay is obviously low here. So lower time delay. And the very important point with the emitter coupled logic is, unlike in the TTL and unlike in the CMOS, so here the emitter coupled logic will be operating with the negative power supply voltages. Negative power supply voltages. So far we have seen that the power supply voltages are VDD is plus 5 volts VDD, the VDD is 5 volts of VDD, and the ground is 0 volts here, isn't it? But now the emitter coupled logic is, it is operating with the negative power supply voltages here. And the another characteristic of the emitter coupled logic is the small voltage swing here. Small voltage swing. There will not be much voltage gap between the high state voltage and the low state voltage here. Practically, even if you see here, a plus or minus of the 75 millivolts here, we will see that one. Plus or minus 75 volts. So if the input voltage is a bit of higher than the 75 millivolts, or if the let's say the voltage is at the at a point of 1.7 volt here, say minus 1.7 volt, because these are all negative voltages. So now if the input voltage is deviated plus or minus 75 volts, there will be change in the output voltage here. So such a fastly it will switching between the states here. Okay, so small voltage swings here. And the another characteristic of this emitter coupled is low fan out here. It is low fan out here. It is low fan out here. So these are all the characteristics of the emitter couple. So now from these characteristics, can you tell what are the advantages and what are the disadvantages of the emitter coupled logic? What are the advantages of the emitter coupled logic and what are the disadvantages, the merits and demerits of the emitter coupled logic? The merit is, advantage is fastest of the all logical families. Out of the all logical families, unipolar and bipolar logic families, it is the fastest here. You know, the propagation delay, I mean that reflects on the speed. The propagation delay is 1 nanosecond for emitter coupled logic, whereas the CMOS logics will have the a propagation delay of the 100 nanoseconds. Even the ECL can have a propagation delay. I mean that the propagation delay, it can have the 500 picoseconds, 0.5 nanosecond. Okay, that is advantage of the emitter coupled logic. And the second advantage is the transistors are operating in the active region. Because of their operating in the active region, so it will not enter into the saturation region. And the another advantage here, it is not specified here, constant current supply. It is the constant current supply here. Constant current supply here. Sorry for that that one. So it is the constant power supply here. That is the another advantage here. Okay, and the fast switching is the advantage, lower time delay is the advantage. Now what about the operating negative power supply voltages? I mean, sorry, the demerits. The demerits is this one, operating with the negative power supply voltages. Usually we use the positive power supply voltages, but here we have to go with the negative power supply voltages. And the another disadvantage is low fan out here. Low fan out. You know what is a fan out? The fan out is the maximum number of gate inputs that can be driven by that single gate output. So for the ECL, it cannot handle more gate inputs here. That is the drawback of the ECL. Okay. So these are all the characteristics of the emitter couple logic. So here we will stop for today. We will stop here. And in this today's session, we have discussed about the low voltage CMOS and low voltage TTL logics and their interfacing. And we have seen the characteristics of the emitter couple logic. So in the next class, we will complete this emitter couple logic so that we can conclude for the first unit. So is it clear? So do you have any questions? So if you have not any questions, then we can end the meeting here. So any questions? Vanessa? Any questions?
No, sir.
Okay. No, so for today, we will conclude here, and tomorrow we will discuss the emitter couple logic. So now I'm ending the meeting. Thank you.